one, hold on, Thursday, and then you have Tuesday. 2 more classes, right? Other than today?
Yes.
Yeah, we will continue because on this Thursday you will have a class and next Tuesday you have a class, but next Thursday, the beginning of midterm. Let's do a review of the FET chapter. FET stands for field effect transistors. It's also an amplifier. Just like BJT, FET is also an amplifier. It has 3 terminals. What are the names of the terminals? Gate, source, and drain. What do you have in BJT? What are the name of the terminals? Base, emitter, collector. This one has 3 terminals named gate, source, and drain. In some ways, the FETs and BJTs are similar. For example, both are amplifiers, both can be used for switching circuits, matching impedance from one stage to the other. But the major differences are below, as shown on the screen. You know BJTs are current control devices. We can see that from the equation IC equals beta IB. So the collector current is a function of the input base current. It is driven by the current. For the FETs, they are not current control devices. They are voltage control devices. The main input parameter is an input voltage. Compared to BJTs, the FETs, they have a very high input impedance. On the other hand, if you look at the gain, especially the gain of the voltage, BJTs tend to have higher gain. FETs, they are less sensitive to changes in temperatures, so better suitable for ICs, integrated circuit. Which parameter of the BJT changes with temperature changing? Do you remember which parameter of the BJT is sensitive to temperature variation?
The stability.
For BJT, which value changes with temperature? It's the beta value. Beta value changes when the operating temperature and surrounding temperature changes. FET is not sensitive to temperature changes just like BJT. But they are more sensitive for static electricity. So when you handle, especially the MOSFET, when you handle them, you have to handle carefully. There are different types of FETs. JFET is the main focus of our course. Junction field effect transistor. There's another type, metal oxide semiconductor FET. D MOSFET is called the depletion type MOSFET. E is called enhancement type MOSFET. D type and E type are subcategories of MOSFET. You can have 2 ways of creating a JFET. You can create an N channel and you can create a P channel. Somewhat similar to BJT, but not exactly same. In BJT, you have NPN or PNP. This one, the main structure is either N-type or a P-type. We call this the channel. And the other type is connected with ohmic contacts. Displayed in front of you is an N-type JFET, N-channel JFET. The 3 terminals, gate, source, and drain, are connected with an ohmic contact. The P-type material, you see there are 2 sides of the N channel. You have P-type material. The ohmic contact is wrapped around. The dashed line is actually going back behind the body. It's wrapped around by P-type material, and then connects with the gate. Drain and source connects to the N channel. The main current flow happens inside the channel. Between P and N, you see a gray region, that is a depletion region. If you try to compare the three terminals of JFET with the water spigot, gate of the water spigot is like the controlling valve. It controls the width of the channel and the flow of current. Source is the excess electron, which is minus charge. And drain is the electron deficiency tunnel. As a result, you have the plus charge. We always use the conventional current flow direction in our course and university. That's why when we draw the circuit, the current is flowing from plus to minus. In real life, it is actually going from minus to plus. Electron flows from an excess point to a deficient point. There are three operating conditions for JFET. What are they? First, the gate source voltage VGS is 0, and then you keep increasing the drain source voltage to some positive value. The second operating condition you can have when you put the VGS, the gate to source voltage, less than 0, which means it's a negative value, maybe -1, -2, etc. But VDS also at some positive value. And the third region for operation we call the voltage control resistor, where the voltage and current relationship is just like Ohm's law, V equals IR. The more the current, the more the voltage, and resistance is increasing as well. The first operating condition, you keep the gate source voltage at 0 and keep increasing the drain source voltage. What is going to happen? The depletion region is becoming wider and wider. At some points of VDS, the two depletion regions will touch each other. If you compare this situation with a physical water channel, it may seem to you that, okay, the channel is blocked, there will be no more flow of fluid. If you compare from that perspective, the channel is blocked, there is no flow of current, but actually the current will flow, but it will not keep increasing even though you increase the drain source voltage. This point is called the pinch-off point. And the voltage, the drain source voltage, where you get the pinch-off, it's called VP in the problem or all the exercises that we have done. At pinch-off voltage, you will reach the maximum current, the drain current. Drain current and source current, they're essentially the same because they're passing through the same path. So at that point, we call the drain current ID equals IDSS. And this is the saturation drain current. If you further increase the voltage, the value will not increase from IDSS. This was a question on your quiz. What happens to the current? What do you call the current at the pinch-off point, and what happens to the current when you increase the voltage? A few of you answered it properly. Some of you were giving me copy-paste answers, which are wrong. All of your answers are the same. You are telling me what happens to the voltage. That was not the question. The question is, what do you call the current and what happens to the current? Anything that is not asked, if you still answer, you don't get marked for that. What happens at a pinch-off? You reach this graph. ID becomes IDSS at the pinch-off voltage VP. We have dealt mostly with N channel. So for that type of JFET, the pinch off voltage is happening at a negative value. You see where VP happens when VGS equals 0 volt. Now if I decrease the gate to source voltage to -1 or -2 and keep decreasing, maybe -3, -4, what will happen? The pinch off will happen earlier. At this point, you get a pinch off. Maybe the pinch off will be earlier than this as you decrease the gate source voltage. Now, apply a negative volt to gate and source, between gate and source. What happens as you keep applying higher and higher negative voltage? The pinch off point is moving left on the graph. When your gate source voltage equals to pinch off voltage, there is no more, you see, there is no perceptible current. When VGS equals VP, ID equals 0. And when, you'll see from the Shockley's equation, what is the equation? ID equals IDSS times 1 minus VGS over VP whole square. The left region of the pinch-off point we call the voltage control resistor because it increases almost linearly. As you keep increasing the volt, the current increases. And when you hit the pinch-off point, the current hits the maximum value. It will not increase any further. We did not do any problem with p-channel JFETs, but the idea is you reverse all the polarity and current direction. The image of any graph will be the mirror image of what you can see for an N-channel JFET. Characteristic graph that we did not use to solve any problems. This is for the P-channel. For the N-channel, the pinch-off voltage VGS, they are in the negative region. This is the symbol of an N-channel JFET. 3 terminals. Gate, source, and drain. ID is same as IS. What is the gate current IG for a JFET? Can someone tell me, remember and tell me, what's the gate current?
Yeah, what do you ask? What is a gate current, right?
Yes, IG, gate current IG equals to what for JFET?
The 0 amps.
0. And what is the reason that we assume IG to be 0? 0 is the correct answer.
Because it came from like G, like the plus sign.
No, that's not the reason. Think about the nature of JFET. On the input side, what does a JFET look like? Input is gate to source. That's the input. Do you know impedance? What is impedance? If you have a high input impedance, what does that look like? A very high input impedance. What's
The current will go down.
The current will go down. What if you have such a high input impedance? If you think in terms of the, first of all, what's the unit of impedance?
Ohms.
So you are using the same unit as resistance. So if you have a very high input impedance, what does it look like? What type of circuit? Open circuit. A very high resistance. You cannot have infinity resistor in reality, but maybe mega ohm, 10 mega ohm, that's very high, that almost no current will flow. On the input side of the JFET, there's a high impedance by nature. So IG is negligible. You can ignore it as to say IG equals 0.
Teacher,
Yes,
like do we like always ignore IG always or sometime?
always IG
Always.
equals 0. So when we have done a few problems in the class where you had a gate resistor RG and the voltage drop IG RG, since IG is 0, we replace the RG with the 0 voltage drop or short circuit equivalent. So the transfer characteristic is quite an important one, and this was also asked in the quiz. I gave you a picture of a blank graph paper, and I asked you to find 4 points to draw the shortcut of this curve. This equation is known as the Shockley equation. I think half of you got it right, but not all 4 points. Some points you made mistake. Some calculated manually. 2 students you calculated manually, and then I think 3 of them. 2 of you were correct, 1 is slightly wrong. There are shortcuts to actually draw this. When ID equals 0, what is VGS? You can find that. When ID equals half of IDSS, what is VP? ID equals 1/4 of IDSS, what is VP? And then when VGS equals VP, what happens? When you answer the question, you say -2, 2. The first parameter is x-axis, the second parameter is y-axis. A few students wrote the y-axis first and then x-axis later. That is not how we write the point in Cartesian coordinate system. 0, 0 means x0, y0. 1, 2 means x equals 1, y equals 2. So on the x-axis here, you have the voltage, and on the y-axis you have current. Please write correctly. A few of them you make this mistake. You see, the relationship between input voltage and output current is not a straightforward one. There's a square term. That's why the characteristic graph of the JFET is not a straight line, rather it's a curve. On this slide, the left-hand curve, the curve to the left of the y-axis. This is the JFET characteristic curve, and then you have to have another set of graphs on the right-hand side. It tells you what happens to the current for different values of VGS, the gate to source. This is the controlling input. If you recall from our last class, BJT also has 2 sets of graphs. When you have 3 terminal devices, you need more than 1 graphs. For a 3 terminal device, it is not possible to fully explain the characteristics of input and output using just only 1 graph. That's why you need 2 graphs. Here it's plotting at different values of VGS what is going to happen to the current. If you also look, when VGS equals VP, the current is 0. It can also be satisfied from the Shockley equation.
Teacher?
Yes?
Like I would like to ask the question like from the quiz.
Yes, sure.
Like on the quiz that you told us to find like the 4 point, like what is like the formula, not to find the 4 point. I still like confused with the graph.
The formula that you are asking me about is this formula. The one that is being shown on your screen, ID equals IDSS1 minus VGS over VP squared. Sometimes the question asks, use the Shockley equation. This is the Shockley equation for JFET characteristic graph.
Okay.
So in this formula, if you put VGS equals VP, what happens? ID is 0, that is 1 point. And if you make VGS equals 0, what happens? ID becomes IDSS, you get the second point. And then I taught you two other shortcuts. What are the shortcuts? If ID equals 1/4 of IDSS, VGS equals what? Half of VP. You can plot that point. And then the fourth coordinate, when ID equals half of IDSS, VGS equals how much? Is it 0.3 times VP? I think it's 0.3 times. So you have 4 sets for quickly drawing the graph. Those are the 4 points you can find from this equation. But you have to remember the shortcuts. When you remember the shortcuts, you don't even have to calculate manually. So are you clear now about this, how to plot the transfer curve?
Yes.
And the formula is already given in the formula sheet, which I was displaying during the exam. Here are some examples of what information you can find on a JFET spec sheet. It is a convention to report everything at room temperature, which is 25 degrees Celsius. So there are some limits. You cannot provide infinity voltage or infinity current, both in positive or negative way. If you exceed the safe limit, the JFET is going to get destroyed. See the value of IDSS when it's turned on. At VGS equals 0, VDS is 15 volt, typically 3 milliampere. There are also maximum ratings from different terminals, from drain to source. Here it says 25 volts. Drain to gate, if you try to apply a voltage, 25. Gate source voltage, it cannot go more than minus 25 volt. That is the limit here. And forward gate current, IGF, 10 milliamp. The temperature range seems to be quite high, minus 55 to 150. So 55 plus 150, 205 degrees Celsius is the range. Seems like a military grade operation. Different electronics, they have different ranges. You have a regular consumer grade, then you have, for example, for medical device and life-saving equipment, it has to have more precision, and for military operation, it has to have another type of range. This one is a P-channel JFET. As you see, the arrow is going away from the gate. When we draw the N-channel JFET, the arrow is coming inside the body of the device. We talked a little bit about MOSFETs in our class. Did not solve any problem. The MOSFET has some special characteristics in addition to JFET basic characteristic, which make them very useful. Two types of MOSFETs, D type and E type, depletion and enhancement. They differ in construction. For the depletion type MOSFET, here it is showing a P substrate. The main body of this MOSFET in this example is a P type. And then you have N-type regions, two N-type regions. joined with a channel made of N-type material. There can be another terminal. There may or may not be. So you have gate source drain, and then you have an additional called the substrate. We call this SS. In between the ohmic contact and the P and N, this region, which is shaded, this is a thin layer of silicon dioxide insulating material. It is so thin, if you are handling the MOSFET with your bare hand and your body generates some static electricity, that electricity can go through this layer and damage the MOSFET. There are some symbols you can read, and then there's an enhancement type. The difference between D-type and E-type is the two N regions are not connected through a channel. And I told you this slide, the publisher made a mistake. It says these N-type regions are connected via N channel. This is not correct. For this, it's wrong. There is no N channel. And then again, it says there is no channel. So contradictory. Maybe they're copying from the same slide. I did not make this slide. I was given these slides from Pearson Education. MOSFET symbol is a bit different. This is an important one, why you should be careful when you are handling MOSFET. They're extremely sensitive to static electricity. Just like I told you a few moments ago, the silicon dioxide layer is very thin. It separates the inside layer of the device from the outside terminals. The layer is so thin, a little bit of electrical discharge can result in current conduction. So always transport in a special bag known as static sensitive bag. There's a static strap which you can wrap around your hand if you are handling MOSFETs. You can apply voltage limiter devices between gate and source so that any voltage passes through is below a dangerous level. This is called a vertical MOSFET, different type of construction. This one provides you a greater surface area. What is the benefit of having a greater surface area? If you have a small surface area and your device is conducting, it also generates heat. The heat does not have enough space to dissipate, which means it is concentrating in one area, increasing the surrounding temperature. It's not good for your device or your motherboard. With vertical MOSFET construction, the surface area becomes larger, which means the heat can be distributed on a wider area. So the heat in a unit area is less. Switching time is faster for vertical MOSFET. This one is called a complementary MOSFET. It uses both P channel and N channel. See, on the left hand side you have two P regions joined with a P channel. On the right hand side you have two N regions with an N channel. Then you have isolated N channel and isolated P channel. And then both of these sub areas are constructed based on an N-type substrate. Used in logic gates, logic circuit designs. For high-speed switching applications, you can use CMOS, complementary MOSFET. We did not do any problems to solve for the MOSFET. There are actually equations. You can have MOSFET problems, but since I did not teach you for this term, I will not ask you in this term. Biasing, there was a question about biasing on the quiz. Only few of you got it right. The question was, what is the reason, why is it necessary to provide biasing to an amplifier? I think more than 50–60% of the students, you copy paste it from somewhere and the answer doesn't make any sense at all. That's not what we The answer will make sense if you give proper explanation, but you just copy paste 2 lines from a book or a website. So the answer does not make sense. You did not get score for that. The reason for providing biasing is to turn on the amplifier so that it can amplify signal. Simple answer, nothing more than that. If you remember my lecture, I also explained it, that the gain for the signal happens due to the power transfer, energy transfer. The average power of an AC signal is 0. You have a positive peak and a negative peak. So all this energy transfer is happening due to the presence of the DC source, and that's why you can amplify signal. If you answered like this, you got full marks. How many types of bias can we provide for JFET? For the case of BJT, we studied 4 biases, which are what? Fixed bias, emitter stabilized, voltage divider, and then the 4th one was collector feedback. For JFET, we studied 3 biases: fixed bias, self bias, and voltage divider. You can also have biases for MOSFET, which we did not study, but the names are self bias and voltage divider for D type, and feedback and voltage divider for E type. So voltage divider bias is a common pattern for all types of FETs. Here are the basic current relationships. We always assume Ig approximated to 0 amp because of the high input impedance. The drain current is same as the source current. Why? If you think about the channel, the N channel, for example, the same current is coming from the drain and it's passing through the source. This is the Shockley equation, ID equals IDSS times 1 minus VGS over VP squared. And the bottom equation is for MOSFETs. If in any term I teach you MOSFET problem solving, then I do it. This time I did not do problem solving for MOSFET. For fixed bias, the biasing point or the Q point is fixed. VGS equals minus VGG. There's a DC source inside the loop between gate and source. That is how the point is fixed. And then the source is connected to the ground. VS is 0. VD should be same as VDS. VD is VDD minus IDRD. VG, some letters are missing. VG is same as VGS, and VGS is minus VGG. For a fixed bias, it is possible to solve the problem entirely using equation and without drawing any graph. But for the other 2 types of bias, it is not possible for JFET. Second type of bias we call the self bias. Each terminal has a resistor of its own. When we do the DC analysis, what do you do to the capacitor? Now we are in the DC analysis. How do we treat the capacitor for DC analysis?
I'll cut it off, open circuit.
Open circuit. Get rid of the capacitor. When you open circuit, the signal cannot come in, no signal goes out. You can ignore, and then you focus on only the middle part. When Ig equals 0, IGRG, which means VG also equals 0. So VGS will be gate to source. You see here is VDD minus IDRD minus VDS minus ISRS equals 0. If you think about the loop, IS is the same as ID. This point is 0. VGS minus IDRS equals 0. I just replace IS with ID. This is the equation. So If RS is a fixed resistor, you have to find different VGS for different values of ID. Also notice the negative sign. There will be negative slope that will start from the origin of an XY graph. This line, when intersects with the transfer curve is the Shockley curve, characteristic curve. It says here, plot the transfer curve using the 2 points and then some shortcuts. When I could not see the picture, where's the picture? This one, for example, this is for a voltage divider. For a self-bias, the black line, the network line starts from 0. You can solve both the input side and output side. For the output side, VDD minus ID RD minus VDS minus ID RS equals 0. So from that, you can find the expression for VDS. It's a KVL equation. Vs is what? From source to ground. The voltage drop, ID RS. Therefore, VGS is negative ID RS. You can also use the double subscript notation for some parameters. Voltage divider bias. There was a problem. There was a problem for BJT on the quiz. I asked you to find the exact analysis. So you had to find the Thevenin resistor, Thevenin equivalent voltage, and a few of you made the mistake of saying that VB is same as ETH. VB is not same as ETH. Not when you are using the exact analysis. ETH, the Thevenin voltage, is found using the voltage divider. VB, you can use the double subscript notation. Maybe this was also a homework. When you have voltage divider bias, if you ignore all the capacitors, VG is what? At this point, VG. VDD R2 over R1 plus R2. This is the voltage divider. On the inner loop, you see VG minus VGS minus IDRS equals 0. Therefore, VGS equals VG minus IDRS. VG is this point. Due to the high input impedance, we say IG is 0. So whatever current is flowing from the biasing DC source, it goes through the second resistor. If you look at the equation, VG is on the positive x-axis and then minus IDRS. If ID is 0, VGS equals VG. This is the point. When VGS equals VG, ID is 0. And then for every value of ID, maybe get 1 or 2 more points, then you can draw a straight line. And this blue curve comes from the JFET transfer curve. When they intersect, you'll find the final value IDQ, the drain current at the operating Q point, and then you can find VGSQ, the gate to source voltage at the operating point. This is the value of ID which you have to use to solve for the rest of the parameters. Any questions?
No.
Sir,
Yes.
in the exam, when finding IDQ, how exact do we have to be with the value?
Well, within 5–10% error is fine, but in some cases I saw that the students, they show the equation, all the steps, and then they got something quite wrong. In that case, you still get credit, not get a 0. However, some students, they don't show any steps at all, and the answers are wildly different, then I had no choice but to give them 0. If you showed me some steps, your concept is fine. Let's say you have one of the voltage value was what, 1.17 volt, and you wrote 1.16 or 1.156. I still take this as a correct answer. It depends on how many digits you take to calculate. But instead of 1.16 or 17, if you write 1.3, that is not quite okay.
Okay,
That's a
makes sense.
huge difference. Most of you got, like when I looked at your BJT problem, a few of you gave me exact answers, some of you gave me close answers, you get points. There were how many parameters? 6 parameters or 4? One parameter you got wrong, some of you got wrong. So 4 times 0.5, each one carried half mark. If you did all 4 correct, you got 2 out of 2. If you got 3 out of 4 correct, you will get 1.5 out of 2. That's how I mark. These are the calculations. It's the same concept. You have an inner loop and an outer loop. You have to use the KVL, the Kirchhoff's voltage law equation, to solve for different parameters and to get an expression for the equation. We did all our analysis with N channel. For P channel, same concept, but you reverse polarity of voltage, direction of current. Graphs will be mirror images. Your exam questions are based on N-channel graphs for this course, because N-channel is the most widely used and it is very common. Some of the applications of JFET are this: timer, network, voltmeter, voltage control resistor. After we finish the DC analysis, first we start with the construction, then we talk about the DC analysis. Now you have to do AC analysis. The end goal is to find the gain of the amplifier. Using the DC analysis, you found the voltage and current at the operating point, but the end goal of an amplifier is to amplify your input signal. For that, you have to calculate the gain, and gain calculation is possible only when you complete the AC analysis. This is just a summary of FET. They have great voltage gain, input impedance is high compared to many other amplifiers. FET, they consume a bit low power and stable over a wide range of frequency. When you do the AC analysis for FET, we came across an important parameter known as transconductance, small g sub m. It is the ratio of output current variation to the input voltage variation. Carefully notice this: is the ID is the drain output current. VGS is the controlling input voltage, and it's delta. So the ratio of change in ID to corresponding change in input VGS we call transconductance. The unit is Siemens, capital S. Why transconductance? This parameter connects input with the output. The numerator is an output parameter. The denominator is an input parameter. GM connects these two using the ratio. You can graphically determine on the transfer curve from the Q point. If you draw a tangent line, there are two ends of the line. These two ends, you can draw a triangle, a right triangle. And on the base, you can see there are two extreme ends of VGS. One is high, one is low, so the difference is delta. And on the y-axis, you have two ends of ID, high ID and low ID, ID max, ID min. The difference is also delta. So the slope at the Q point is also the ratio of delta ID and delta VGS. You can take the slope of this tangent line, and you see this is a positive slope. It is going up and right. This is a positive value. GM, you will have the positive value. You will not have the negative one. There are different ways of expressing. You can write 2 times IDSS divided by the absolute value of VP, because sometimes VP is minus, especially for N channel, and then multiply by this thing. This term outside 2 IDSS over VP is called GM0. It is transconductance at 0 volts VGS. GM0, then GM equals GM0 times this. You can also find in terms of the current and the saturation current. For JFET, the input impedance, FET input impedance is infinity ohm, which is like an open circuit. Output impedance is given by a term called small rd. When you do not connect with anything, by default there's an output impedance. It is not the opposite of transconductance. Sometimes you might want to take 1 over GM, that is wrong. CRD is the ratio of output voltage variation and output current variation. It's not gate source voltage. Gate source is kept at constant. On many spec sheets, YOS is given. It is called admittance parameter. Admittance. It's typically listed on the spec sheet. So the output impedance has nothing to do with the inverse of transconductance. It's a common misunderstanding. Please be mindful of this one. We have a model, AC equivalent circuit or a model. There are several steps of creating this model in the textbook. I don't usually ask questions and I didn't teach that, but this is the basic model. The source is on the ground. Input side is gate source, output side is drain source. As you can see on the input side, gate and source is not connected. Because of the high input impedance, it is like an open circuit. But you can have a voltage on the open circuit, so you have plus minus VGS. On the output side, you have output impedance, small rd, and then there's an equivalent current source, which is GM multiplied by VGS. The drain source voltage polarity is taken plus on top, minus on the bottom. So it implies the current should flow from left to right, but it is flowing from right to left. Because of that reason, we can say that between input and output, there's an 180-degree phase shift. Also for the FET, same as the BJT. So when you do the gain calculation, the gain is a minus parameter. How do we do the AC analysis of a JFET? Let's say you're given, this is a fixed bias. A fixed bias, the Q point is set by this biasing voltage. VGS equals minus VGG, and RG, when you say IG times RG, it becomes 0. The voltage drop is 0. How do we analyze? We short the capacitor for AC analysis and kill the source. If you kill the DC source, it goes to the ground. So RG goes to the ground on the input side. On the output side, RD, we have to ground VDD, kill VDD. RD also goes to the ground. And then you throw the model in the middle. Try to look from the input side of the circuit. You see input impedance is same as RG. Typically, RG is given in mega ohms. So it satisfies the gate current 0 condition, which is the approximation. If you look from the right-hand side back into the circuit, you see two resistors in parallel, big RD parallel with small RD. There are cases where you can ignore the small RD. What are the cases? If small RD is greater than or equal to 10 times big RD, then you can ignore it. So here the input impedance is RG, output is RD parallel small RD. What about the voltage gain? Voltage gain is output voltage divided by input voltage, given by minus Gm times RD parallel with small RD. And you can ignore small RD when you satisfy that condition. Is there a current gain mentioned for JFET? No, we do not mention or define the current gain. First of all, it's a voltage control device. Therefore, the current gain is not a matter of concern. Secondly, when you choose IG, input current IG is 0. If you divide the output current by input current, divide something with 0, it becomes infinity. So that will be an undefined parameter or undefined equation. For a self-bias, same thing. But if you remember the effect of shorting a capacitor, this bypass capacitor CS shorts out RS. Everything else is the same, they stay in the circuit. So self-bias and fixed bias, input and output impedance, the same type of equation. You have the next is voltage divider bias. You can guess what happens in this case. On the input side, you have two resistors R1, R2 in parallel. That is your input impedance. The output impedance will be just RD parallel with small RD. RS is shorted out. Sometimes the capacitor is unbypassed, then equation becomes more complicated. This one. All right. So I do not want to review another chapter today. Maybe what I can do is bring you to the quiz. Can we look at the quiz that we just had and discuss the answers?
Yes.
Okay, we'll discuss the quiz. Let me load it from my browser. Once it is loaded, I'll switch the screen. And I'll take attendance. I'm taking attendance for every class until before the midterm. It takes a bit time to log in to AU using the Chrome browser. That's why I'm still trying. Okay, it's loading slowly. What the heck? Okay, I have to go to Google Forms. And now I'm ready to switch the screen. Do you see the quiz one on the screen?
Yes, we can see it.
Let's look at the first one. What voltage value would show across the load resistor when the zener is connected parallel to it? Zener is turned off, but the series input is conducting current. The correct answer is the value will be determined by the voltage divider equation, Vs times RL divided by input resistor plus RL. Someone said that it is the same value as the voltage drop across the input resistor. Someone said that it is same value as the input voltage source. It is definitely not same as input voltage source. It can be the same value of the voltage across input resistor when I say both the load resistor and input resistor they're equal, but this one doesn't say that. So correct answer is the voltage is determined by the voltage divider, input voltage times RL divided R plus RL. I did not give you any number, so you could try to guess that it is expressed in terms of equation. Second question was why the emitter stabilized bias circuit is more stable than the fixed bias. And I'm afraid, I think almost 100% you are giving me copy paste from somewhere which I didn't even bother to look, because all your wording and even the full stops, commas are the same. And you are talking about stable base current, with the exception of maybe 2 students gave the right answer. We are concerned about the stability of output collector current and output collector emitter voltage when the beta varies with temperature. But everyone is talking about stabilized base current. In some ways it is correct, but you had to explain further. If you have stabilized base current, what does that do to the output current? That part you did not tell. I gave you maybe quarter marks, 0.25, for saying the half part, but I should not be. When everybody's answer is the same, obviously it is something wrong there. It is a suspected of cheating. In the midterm, I will not be that liberal. Explain why it is necessary to apply DC biasing, which we just discussed in today's class. What does MOSFET stand for? Metal oxide semiconductor field effect transistor. Almost all of you got it right. Okay, given IDSS 8 milliamp, VP is -4. Determine the 4 points. You don't need to draw, just tell me the points. Shockley's equation, it says. Okay, when VP is VGS equals VP, which is 0.4, ID is 0. This is 1 point here where I'm putting the mouse cursor. When VGS equals 0, ID equals IDSS. So another point is right here. Can you just join these two with a straight line? No, you need at least one more point to draw a curve. When ID equals 1/4 IDSS, which means 2 milliamp, VGS is half of VP, means here -2 volts. So -2 is 1 point. This point is called -4, 0. This point is called 0, 8, not 8, 0, 0 and 8. This one is called -2, 2, this point. 3 points are enough, but since I asked you for the fourth one, some of you did manually and then your answer is correct. I checked it. The fourth shortcut is when ID equals half of IDSS, which means at 4 milliamp, VGS equals 0.3 times VP. What is 0.3 times 4? -1.2. Here you made another mistake when you wrote. You wrote plus 1.2. I did not give score for that. It's a minus sign. So for 4 milliamp, minus 1.2 is around this point, just approximately. If you are given a graph paper with pencil or pen, if you found these points, you would draw a very nice curve. Any question about this one? Any further questions? Seems like no questions for this one.
No.
The next one is diode circuit. There were two circuits. When you have a circuit like this, the first thing to do is determine whether the diode is on or off. Let's see. This silicon, the anode is here, and you're applying a plus voltage. So most likely it is on. The minus voltage is here. There's a little bit of voltage drop. 12 minus 0.7. This point is 11.3. Most of you got it right. And then there'll be current passing through. When the current passes through, polarity is plus minus. Gallium arsenide possibly also on. So this one is 1.2. When it's turned on, 1.2. VO2 is just from this to ground. It is 1.2. For the circuit B, the second circuit, what is happening? You have a minus volt, but this is anode. So germanium is reverse bias. It is an open circuit. Once it is an open circuit, the rest is, they are not having any current at all. If there's no current, there's no voltage drop. Here you have silicon, you have germanium, here you have minus 10. So if the VO1 was just after minus 10 volt, you could say VO1 is minus 10 if you put the probe here, but the probe is right here. It is not sensing any voltage drop as there is no current. Germanium is open, and it doesn't matter because once this is open circuit, the rest does not get anything. This point, you have 0 volts, and there is no current flowing at all, so the voltage drop will be 0, V02. Vout2 is 0 volt as well. Once you figured out the diodes are off, the rest is very easy. What do you call the drain current that occurs at the pinch-off point for JFET? The answer is, it is called the IDSS, the drain to source saturation current. If you wrote just IDSS, still okay. Half mark for that. But some students, they say it is called the pinch-off voltage. I did not ask about the voltage. I asked, what do you call the current? Second part of the question, what is the effect on this current when you increase the drain source voltage? So what happens to the current? It stays at this level. At this point, it says at this point when you increase the voltage. It stays at this level, and even though you increase the voltage, it does not go up or down, constant. Another question, where is the location of the depletion region in a two-terminal diode? You can say it is at the junction. You can say it's in the middle of P and N. You can also say it is in the part where P meets the N-type material. But it is not at the terminal. It's not outside. What happens when to this region when the diode is reverse biased? The correct answer is the depletion region becomes wider in reverse bias. If you wrote just these two, you got 1 out of 1. Given the voltage divider configuration below, determine 6 things. Each carries 0.5 marks. What is beta times RE? We have to solve a condition, but here you have approximate you have to do the exact analysis. Can we satisfy the condition, you think? You have R1, R2, and you have to satisfy beta RE must be greater than or equal to 10 R2. So beta is 80, RE is 0.68. How much is beta RE? 80 times 0.68, how much is it? Is it 54 kilo ohm about? I don't have my calculator. What is beta RE?
54.4 kilo ohm.
Yeah, I was doing in my mind. It is about 54. Beta RE, is it 10 times, is it greater than or equal 10 times R2? 10 R2, this is R2. What will be 10 R2? 91 kilo ohm. Definitely not equal and definitely not greater. So if you try to do approximate analysis, you will be wrong for all answers. You have to use the Thevenin. This is the key to understanding. Sometimes in the question, it is mentioned, use this analysis or that. This one does not mention. You have to check the condition first. So first thing is to find Thevenin voltage. ETH is VCC R2 divided by R1 plus R2. I have my solution sheet here. It's 2.05 volt. Most of you got it right. And then Thevenin equivalent resistance when you kill the source is R1 parallel R2, 7.94 kilo ohm about. And you can use the equation for voltage divider. What is the base current, IBQ? It's ETH minus VBE divided by RTH plus beta plus 1 RE. Also on the formula sheet. The correct answer for base current is 21.42 microamp. ICQ, just simply beta times IBQ, 1.71 milliamp. And VCE at the Q point, once you find ICQ, you know it's VCC minus ICQ times, in the bracket, you add the two resistors, RC and RE, 3.9K and 0.68K, around 8 point something, 8 point, I can't remember, 8.3 or 8.6. VC at this point, VC is VCC minus IC RC, only at this point, voltage drop. Comes to about 9.3 volts. What is VE? From E to the bottom you have ground, so you could just say IERE or ICRE, around 1.16 volts. And then the last one is asking VB. VB is not ETH. If you do the exact analysis, VB is not ETH, but if you do the approximate analysis, VB is at this point. VB is VE plus VBE. So if you look at this loop, you can say VB minus VBE minus VE equals 0. So VB is the base emitter voltage, which is 0.7 plus VE, which you found out it is 1.16 or 17. VB is approximately 1.87 volts, not 2.05. Many you got it correct for VB, some you got it wrong. That's why I had to mention. In your midterm is on January 18. I will create a calendar event on January 18 from 9 to 11 on Microsoft Teams. You have to join on that calendar. There are 39 of you. And then I have 4 other students from another subject, same time conflict. So I will bring them in the same room. I'll proctor all the students in the same room. I have been doing this for the last 3 semesters. Every time my 2 exams are at the same time. There were 3 time conflict students. 2 of you have already rearranged with your other teachers. 1 you could not, so your exam will be locked. You cannot see the exam during the other students are taking, but once they are finished, then you can join in. Immediately after that, I think I already told you in a message, group message for the 3 students. There is only one part in the exam. There are no part 1, part 2. You will have 11 questions similar to this from diode, BJT, JFET, and op-amp. 11 questions, 2 hours to complete. Some are quite small, some are medium. Large questions, I would not call them very large. Small, medium, large, but not something that you spend a lot of time, so that you can have some time to review, and you have to do sequentially. The questions are coming from a random question bank. Same question, but you don't see the same question at the same time. Different students see different questions at the same time. You cannot go back to a previous question. You cannot hit the browser back button. So if you think you solve something later on, no, you cannot do that. You have to pass through sequentially. This is the rule set by academic affairs when you do the exam for online. What else? I will give you the instruction. About a week before the exam, I will create a PDF file, same like in your quiz, on how to prepare for the LMS exam and what equipment you should have. In the next class on Thursday, we have op-amp to do a review. I'm going to take the attendance now. Did you have any questions?
Teacher, about the midterm exam. So there will be 11 questions, and the type of question will be typing and
you have to type, yes.
Problem.
Solving problem type, giving me short or medium answers. The formula sheet is given. With every question, you will see the link to download the formula sheet. So I don't have to show my screen, but I'll have to see your screen. All of you, you should be displaying your screen with the camera zoomed in.
So it's the same type question as we have in quiz 1, right?
Quite similar, yes. See, some you have to calculate and solve, some you have to tell the point, some you have to give me the reason. There's a mix of all 3 types. Not every question is a problem-solving question, as you can see. Some you have to tell from your memory, your knowledge.
Thank you, teacher.
Welcome. Let me start calling Balan.
Yes, sir.
Tilawut.
Yes.
Napatra.
Yes.
Pakon.
Yes, sir.
Raji.
Yes, Ajahn.
Jonikan.
Yes ค่ะอาจารย์
Michelle. Is Michelle here? Not here. Jonikan is here, Michelle is not here. Phil. Silicon.
Yes.
Wisalut.
Yes, sir.
Yucheng.
Yes, teacher. Yes.
Sisihan.
Yes, Ajahn.
Atampong.
Yeah, how?
Tongsu.
Yes, sir.
Martin.
Yes, Ajahn.
Kolawit. Is Kolawit here? Which are you?
Yes, Cap, I'm here.
Jimma.
Yes, Ajahn. Here.
Sonyuan.
Yes, I'm here.
Satawat.
Yes.
Yapeng.
Yes, teacher, I'm here.
Seni.
Yes, present.
Siripop.
Yes, sir.
P2.
Yes, I'm here.
San An.
Yes.
We have Waramet,
Yes.
Warapat,
Yes, Ajahn.
number 1,
Yes, I'm here.
Nathapok.
Yes, I'm here.
Yeah, Warapat I call already. Naptaya,
Yes.
Pichayapong,
Yes, sir.
Komchan. Komchan, are you here? IJK. No, he's not here today. Oh no, he's here. Piradon,
Yes, I'm here.
Kitsanapong,
Yes, I'm here, sir.
Atithya,
Yes, sir.
Tasin,
Yes.
Sukaina,
Yes.
Sirin,
Yes, teacher.
Min Luin U. Min Luin is absent. See you on Thursday.
Thank you, Ajahn.
Thank you.
Welcome.
Thank you, sir.
Thank you, Ajahn.
Okay.
Thank you, Ajahn.
You're welcome. See you on Thursday.
Teacher,
Yes.
can I have a question?
Yes.
In the RMS we can attach the file, right?
You can what?
I mean, during the quiz it takes like a lot of time to type in, so it's not possible
Yes,
for us to.
You get a lot of time.
So,
2
so,
hours. The exam is 2 hours.
so it's not possible to write in the paper and then attach to RMS, right?
No, we don't. I'm not receiving paper submission.
Oh, okay.
You can have a pen and paper if you want to calculate quickly, but you have to type your steps inside the LMS.
Okay, teacher. Thank you so much.
Welcome.